Welcome to my 23rd tutoring session in A-level chemistry. In this video, you will learn about periodic trends in electron affinity. Please take a moment to watch my previous videos on topics periodic trends in atomic size, periodic trends in ionization energies, periodic trends in electronegativity, effective nuclear charge, and shielding effect in group 2 elements. These videos will provide you with a better understanding of this video content. Link to these videos given in the description below. Watch the videos. Don't forget to subscribe my channel, share, like, and watch my full video. What is electron affinity? Atomic electron affinity is the energy change that occurs when an atom in the gas phase gains an electron to form a negative ion. Electron affinity is a measure of the atom's ability to accept an additional electron. Electron affinity can be either positive or negative, and the value depends on the type of atom receiving the electron. Now, exothermic process is shown by a negative sign, while the endothermic process is shown by a positive sign. Let me explain the exothermic process with respect to fluorine atom and endothermic process with respect to nitrogen atom. A fluorine atom in the gas phase gains an electron to form a negative fluoride ion, and its value is minus 332.2 kilojoules per mole. So this is the amount of energy released during the reaction, and the negative sign shows that energy is released when the fluorine atom accepts the electron, and therefore it is an exothermic process and it is a favorable reaction. Now let me explain why it is an exothermic process and reaction is favorable. Now fluorine atom has a total of 7 valence electrons, and it needs an additional electron to complete the outermost shell. Now the positively charged protons attracts the negatively charged electrons. Now fluorine has a total of 9 positively charged protons in the nucleus. It attracts the negatively charged electron to complete the octet, and the incoming electron occupies the outermost electron. Now in the process, the negatively charged electron, when it approaching, the kinetic energy of the electron is converted into electric potential energy, and this energy has to be released in order to retain the stability of the atom, and therefore the energy is released, and this released energy is measured in kilojoules per mole, and it is shown by a negative sign. Therefore it is exothermic reaction because energy is released. So exothermic reaction is always shown by a negative sign. So after the fluorine atom gains an electron, it forms a negatively charged fluoride ion, and energy is released in the process. And why the reaction is favorable? So you have understood why the reaction is exothermic, but why it is favorable? It is favorable because after the reaction, the unstable electronic configuration of fluorine has changed into a stable electronic configuration. That is to say, after the fluorine atom has accepted an electron, its stability has increased. So unstable electronic configuration of fluorine is converted to stable electronic configuration after the fluorine atom accepts an electron. What about the endothermic process? Let me explain the endothermic process with respect to the nitrogen atom. So nitrogen atom accepts an electron, it forms a negative ion. But here we observe that electron affinity value in case of nitrogen is it's a positive value, indicating it is a endothermic process. Why the reaction is endothermic in nature? Let's find out. Now in case of nitrogen atom, energy is required. You need to add energy. So energy is required to add an electron to nitrogen atom. So it is an energy demanding process, because you have to force an electron into the stable atom. So nitrogen, it has a stable half-fill electronic configuration, and after the addition of electron, it attains a unstable electronic configuration, and therefore it is an endothermic process, energy demanding process, and you have to force or push the electron into the outermost shell of nitrogen atom, and therefore it is not favorable. The reaction is unfavorable, indicated by a positive sign, meaning it is an endothermic process. Now here are some highlighting features of electron affinity, atomic electron affinity, and one should be familiar with this 5 highlighting features before they study the periodic trends in electron affinity. So what are those? So let me walk you through this 5 highlighting features. Now electron affinity is a fixed property of an isolated gaseous atom. For example, fluorine, it has an electron affinity value of minus 328 kilojoules per mole, and chlorine, it has a value of minus 349 kilojoules per mole. So these values are fixed. So when the fluorine atom accepts an electron, it releases a specific amount of, a fixed amount of energy, that is minus 328 kilojoules per mole. And while chlorine atom accepts an electron, it releases a fixed amount of energy, that is minus 349 kilojoules per mole. So electron affinity is a fixed property of an isolated gaseous atom. So energy is released when an electron is added to the non-metal like fluorine, and this is shown by a negative sign. That is an exothermic process, which I just explained. But not necessary that always it has to be an exothermic process. When electron is added to an atom, it could go either ways. Either it can be exothermic process or endothermic process. So adding an electron to an atom does not always result in the release of energy. For example, adding an electron to elements like beryllium and nitrogen is an endothermic process and requires energy input. An endothermic process is shown by a positive sign or a positive electron affinity value. And electron affinity is a measurable physical quantity with units. It can be measured in kilojoules per mole. And another important feature is that the element with a more negative value will have a higher electron affinity. So chlorine will have a higher electron affinity because it has a more negative value as compared to fluorine. So one needs to remember all these 5 important points before going to details of periodic trends in electron affinity. Now when dealing with electron affinity values, you should look at what happens to the stability of an atom after an electron is added. Now when you add an electron to an atom, there are only 2 possible things that can happen. Number 1, it can lead to an unstable electronic configuration, which will be a endothermic process shown by a positive value. The other possibility is, after adding an electron to an atom, it can lead to a stable electronic configuration. That is to say, the stability of the atom will increase, and this will be exothermic process shown by a negative electron affinity value. So one should look at what happens after adding an electron to isolated gaseous atom, and later you have to check the electronic configuration, and only after checking the electronic configuration you will come to know whether it is stable or unstable process. That is to say, it could be either exothermic or endothermic in nature. For example, On adding electron to beryllium atom, it will be endothermic reaction, energy demanding process. This is shown by a positive electron affinity value. An example for exothermic reaction will be, which we have already discussed, addition of electron atom to the fluorine atom. It's an exothermic process shown by a negative electron affinity value. So these were the two examples for exothermic and endothermic process. So beryllium for endothermic process and fluorine atom for exothermic process. Now why it is endothermic in case of beryllium? Now beryllium initially it has a stable electronic configuration 1s2 2s2 with the 2s subshell completely filled with electrons. So when you add an electron, it becomes unstable. So after you add an electron to beryllium, it becomes unstable, and you have to add an electron to an higher energy level. You have to add electron to the p orbital, which is at a higher energy level. So unstable electronic configuration is 1s2 2s2 2p1. So in case of fluorine atom, it has an unstable electronic configuration with partially filled p orbital. 1s2 2s2 2p5 is the electronic configuration. After adding an electron, it becomes or attains a stable electronic configuration 1s2 2s2 2p6, where the outermost shell is completely filled with electrons, total of 8 electrons. So what is the driving force for the atom to gain an electron, or why should an atom gain an electron? So atoms become unstable if their outermost electron shell is incomplete, or if the atom lacks a complete outer shell of electrons, like in case of fluorine atom. So the driving force for the atom to gain an electron is to increase its stability or to attain a stable electronic configuration. So an atom accepts an electron if it has a unstable electronic configuration, if it has partially filled orbitals, and atom accepts electrons to increase the stability, increase its stability. And these are some of the examples of elements with unstable electronic configuration or elements with partially filled orbitals. Like in case of lithium, the 2s orbital is partially filled. In case of boron, carbon, oxygen and fluorine atom, the p subshell in the second energy level is partially filled. And in what circumstance atom does not accept an electron? When it has a stable electronic configuration. So when atom has a stable electronic configuration, it does not accept the electron. Like elements having stable half-filled or fully filled orbitals. Like in case of beryllium, nitrogen and neon. So your neon is a noble gas with a stable electronic configuration where the outermost shell is completely filled with electrons. And nitrogen has a half-filled orbital, half-filled p orbitals, which is stable due to symmetry, and beryllium has a fully filled 2s subshell. So let us look at the orbital diagrams for the atoms with partially filled orbitals. Lithium atom, atomic number 3, you find the 2s orbital is partially filled. Boron, atomic number 5, you find the 2p orbital is 2p subshell is partially filled. Carbon atom with atomic number 6, you find the 2p subshell is partially filled. Oxygen with atomic number 8, you find the 2p subshell is partially filled. Fluorine atom, again, it is partially filled and it needs just one electron to attain a stable electronic configuration. And what about atoms with stable electronic configuration? Beryllium, atomic number 4, is 2s subshell is completely filled with electrons. Nitrogen, its 2p orbitals is half filled. You see a symmetry there, and therefore it has a stable electronic configuration. And neon is a noble gas with a stable electronic configuration, where the outermost shell is completely filled with total of 8 electrons. So these are the reasons why an atom accepts an electron and an atom do not accept an electron. Now taking a look at the periodic table. So what is the general trend? Periodic trend in electron affinity. The electron affinity increases across a period as you move from left to right in the periodic table, and the electron affinity decreases as you go down a group. But there are few exceptions to the electron affinity values as you go across a period and down a group in the periodic table. Like in case of beryllium and boron, carbon and nitrogen, fluorine and chlorine, oxygen and sulfur. So why it is so? I'll explain in detail later in the video. Now looking at the period 2 elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. So the general trend is that electron affinity increases across a period. But the actual order is this with reference to the period 2 elements. So here we are talking about only with reference to the electron affinity with reference to the period 2 elements. Now this is the correct order. Neon is less than nitrogen, less than beryllium, less than boron, lithium, carbon, nitrogen, oxygen and fluorine. Why? Because neon has a stable electronic configuration. Neon, nitrogen and beryllium, it has a stable electronic configuration and becomes unstable on addition of electrons, leading to an endothermic reaction shown by a positive electron affinity value. While in case of boron, lithium, carbon, nitrogen, oxygen and fluorine, it has a unstable electronic configuration and becomes stable on addition of electron. It's an exothermic process shown by a negative electron affinity value. So what you see in the periodic table is the order before adding an electron. And the correct order is this. And this is the order after adding an electron. So you should always consider the order after adding an electron, not before adding an electron. So you should not consider the order going by the periodic table. So consider the order after adding an electron, not before adding an electron. Now going down the group, you know the trend, electron affinity value decreases. But you find that period 3 elements, some of the period 3 elements have a higher electron affinity value as compared to period 2 elements. Like for example, group 6 elements, oxygen and sulfur. So oxygen, sulfur should be having a lesser value than oxygen, because going down the group, the electron affinity value decreases. But it is the other way around. Oxygen has less value, sulfur has higher electron affinity value. The same for group 7. Fluorine has a lesser value, fluorine has a higher value. So the general trend going down the group is it decreases, but exceptional behavior is shown only by the first 2 elements. So order is same going down the group, order is correct, but exceptional behavior is shown only by the first 2 elements. So this is applicable for 4 groups, that is group 4, group 5, group 6 and group 7. So which element has the highest electron affinity? Carbon or nitrogen, beryllium or boron, fluorine or chlorine or bromine or iodine, oxygen or sulfur. You will find the answer for all these questions by the end of the video. Now here's a table summarizing the electron affinity trend in the period 2 elements. So here in the table you will find the period 2 elements with their respective atomic numbers, their electronic configuration, and their stability after adding an electron, its electron affinity values, and also whether after adding an electron, whether it leads to an exothermic or endothermic reaction. So let's start with lithium. So lithium electronic configuration is 1s to 2s1. After adding an electron, so where does the electron go to? The added electron goes to the 2s orbital. So that leads to a filled 2s subshell. So it has attained a stable electronic configuration. And therefore, that is reflected in the electron affinity value below. So minus 60 is the electron affinity value. So it has a high electron affinity value. And therefore, it is exothermic reaction, which is favorable. Beryllium, its electronic configuration is 1s to 2s2. And after adding an electron, the added electron goes to the 2px orbital, which is at a higher energy level as compared to 1s and 2s orbitals. So the electron added goes to a higher energy level, and therefore it's an energy demanding process, and this leads to an unstable electronic configuration. It is an endothermic process shown by a positive electron affinity value. Boron electronic configuration is 1s2, 2s2, 2p1. Added electron goes to the 2py orbital. Now here, though the electron is added to a higher energy level, the added electron goes to a empty orbital and there is no repulsion. So since the added electron is occupying an empty orbital, there is no repulsion. And one more factor is that it is very close to achieving a stable half-filled electronic configuration. That is one of the driving force. And therefore, it has a partial stable electronic configuration, and that is reflected in the value, electron affinity value, negative value, exothermic in nature. So it is not completely favorable, but partially it is favorable. Carbon electronic configuration is 1s to 2s to 2p2, and after adding an electron, so where does the added electron go to? The added electron goes to the 2pz orbital, and this leads to a stable half-filled electronic configuration. You can see a symmetry in the 2p orbitals, and this is reflected in the electron affinity value. You can see compared to the previous three atoms, lithium, beryllium, boron, it has a high electron affinity value. It is an exothermic process. Why it is a high value? Because it has a stable electronic configuration, stable half-filled electronic configuration. What about nitrogen? Electronic configuration 1s to 2s to 2p3. After adding an electron, where does the added electron go to? The added electron goes to the 2px orbital, which is already occupied by an electron. So there is already an electron present in the 2px orbital. So this added electron leads to repulsion. So there is repulsion between the previously present orbital and the added electron. So there is electron-electron repulsion in the 2px orbital, and this repulsion decreases the stability of the atom. It is an energy demanding process. You have to force the atom, you have to force or push the electron into a 2px orbital in order to overcome the repulsion. And this is reflected by a positive sign. It is an endothermic process, leads to an unstable electronic configuration. Oxygen 1s to 2s to 2p4. After adding an electron, where does the electron go to? It goes to the 2py orbital. So though there is electron-electron repulsion, so there is two pairings. You can see there is pairing in the 2px orbital and there is pairing in the 2py orbital. So though there is two pairings, though there is repulsion in the two orbitals, the effective nuclear charge increases. So there is in case of oxygen atom, effective nuclear charge is more, atomic size is less, and the oxygen atom needs just 2 electrons to complete the octet, and therefore it is highly stable after adding an electron. Not completely stable, it is stable to some extent because of its small atomic size, higher effective nuclear charge, and it needs just 2 electrons to complete the octet. Leads to a stable electronic configuration with electron affinity value of -142. It's an exothermic process. What about fluorine? After adding an electron, where does the electron go to? It goes to the 2pz orbital, and that leads to a stable electronic configuration. So fluorine atom, after adding an electron to the fluorine atom, it achieves a octet. It forms a full octet, achieves a stable electronic configuration as that of the noble gas neon, which is nearest in the periodic table. Stable electronic configuration. It has a high electron affinity value in the period 2 elements. So among the period 2 elements, fluorine has the highest electron affinity value. Exothermic nature. So when you compare and contrast the electron affinity values of oxygen and fluorine, you will find that there is twofold increase in the electron affinity value of fluorine, because that correlates with the theory that oxygen atom just needs 2 electrons to complete the outermost shell. So it is very close to the octet, achieving octet. So oxygen is close to achieving octet by 2 electrons, and fluorine is close to achieving octet if it receives only 1 electron, which is reflected in the electron affinity values. Now going by the trend, electron affinity increases across a period. So period 2 elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So you can see the size decreases and number of shells remain constant. So what about the number of protons? The number of protons increases as you move across the periodic table from left to right. 3 for lithium, 4 for beryllium, 5 for boron, 6 for carbon, 7 for nitrogen, 8 for oxygen, 5 protons in the nucleus of fluorine atom, and neon, noble gas, has a total of 10 protons in the nucleus. So the number of protons increase as you move from the left to right in the periodic table, and therefore, as the number of protons increase, the Coulombic force of attraction, that is the electrostatic force of attraction between the more number of protons as you move across the periodic table and the negatively charged electrons, incoming electron, increases, which occupies the outermost shell. So remember, the incoming electron is occupying the outermost valence shell, and as a result of the Coulombic force of attraction exerted by the positive charged protons, the electron affinity value increases because of an increase in the effective nuclear charge. So what about shielding? So you need not worry about the shielding, because shielding is constant, because all the elements in the period 2 have just 2 shells, and there's decrease in size because of the increase in the effective nuclear charge. And what about the number of valence electrons? Lithium has 1, beryllium 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon, being a noble gas, it has a stable electronic configuration with full octet of electrons in the outermost shell. So what you observe here, so atoms close to achieving a full octet will exhibit higher electron affinity values. For example, fluorine. So fluorine, it has a high electron affinity value as compared to other period 2 elements, because it just needs 1 electron to complete its octet. And oxygen is less than fluorine because it is short by 2 electrons to complete the octet. So these are the electron affinity values of period 2 elements. But as per the general trend, it should increase across the period. But we see that the trend is not proper, because so as per the trend, electron affinity should increase as the atom gets closer to having a filled valence shell. But some elements in the period 2, they show some exceptional behavior. They show some anomalous behavior with a positive sign, like in case of beryllium, nitrogen, and neon. And why do they show a positive sign? Endothermic process, because these 3 elements have a stable electronic configuration. Beryllium has a fully filled 2s orbital, nitrogen has a half filled p orbital, while neon has a stable electronic configuration with the outermost shell completely filled with 8 electrons. So because of the stability, remember, if the atom is stable, it will not accept the electron easily. Only if the atom has a unstable electronic configuration, it will accept the electron. So as you move across the periodic table, electron shells remains constant, and because of the increase in the effective nuclear charge, the atomic radius decreases and shielding is constant, which is favorable. Atomic size decreases, effective nuclear charge increases, and as you move across the periodic table, the electron affinity increases. But there are few exceptions to this that is shown by lithium, beryllium, boron, and nitrogen. So these are the exceptions, and they show anomalous behavior. So why they show anomalous behavior? I'll explain it later in the video in detail. And stable electronic configuration. So this is the most important factor. So remember, atoms with stable electronic configuration will not accept the electron easily. Only atoms with unstable electronic configuration will accept the electrons. Now let's take a closer look at the electron affinity trend in period 2 elements and take up some practice questions. So what are the two questions in case of period 2 elements? So which element has more electron affinity? Lithium or beryllium? Beryllium or boron? Let's find out. So if you go by the periodic trend, the electron affinity value should increase across a period. So electron affinity increase across a period because of increased effective nuclear charge, decreased size of the atom, shielding is constant, and the atoms are closer to achieving octet. So these are the four major reasons why the electron affinity value should decrease. So this is expected. This is the expected trend. But what actually happens is that, so exceptional behavior shown by beryllium when compared to lithium and boron. So first there is decrease, then increase. So decrease in case of lithium, then increase in case of beryllium, and then again decrease in case of boron. Why is that? Let's see. Now the unstable electronic configuration of lithium is 1s2, 2s1, 2 electrons in the 1s orbital, 1 electron in the 2s orbital. Now the added electron, it goes to the 2s orbital. So addition of an electron leads to a filled 2s subshell with stable electronic configuration 1s2, 2s2, and that is why it is a exothermic process shown by a negative sign, negative value of minus 60 kilojoules per mole. And what about beryllium? Now beryllium already has a stable electronic configuration 1s2, 2s2, 2 electrons in the 1s orbital, 2 electrons in the 2s orbital. So it has a stable, fully filled electronic configuration. Now when you add an electron, you will be adding an electron at a higher energy level. So more energy is needed to add an electron to a 2p orbital or 2p subshell, which is at a higher energy level. It is an energy demanding process, which is reflected by the positive sign. And therefore, it is an endothermic process in case of beryllium. And that is why the value changes. So you need to force or push an electron to beryllium atom because it has a stable electronic configuration. That is one reason. And you have to add an electron, or you are adding an electron to a higher energy level. That is another reason. And in case of boron, electronic configuration is unstable, 1s2, 2s2, 2p1, 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and you find 1 electron in the 2px orbital. So the add electron goes to the 2py orbital. So here you are adding an electron to a empty orbital, needs less energy, because there is no repulsion. There is no electron there to experience a repulsion. That is one reason. Another reason is that it is just short of 2 electrons to complete the stable half-filled configuration, electronic configuration. And that is why it is shown by a exothermic value, negative sign. And two more practice questions relating to electron affinity trend in periodic 2 elements. So which element has more electron affinity, carbon or nitrogen, oxygen or fluorine? So going by the periodic trend, electron affinity should increase across a period because of increase in the effective nuclear charge, decrease in size, atomic size, shielding is constant, and elements are very close to achieving the octet. So this is the expected trend. But what actually happens is that carbon has a higher value, nitrogen has a lower value, again oxygen has a higher value. So why is this? Why this anomalous behavior shown by these elements? Let's find out. So the unstable electronic configuration of carbon is 1s2, 2s2, 2p2, 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and the 2p orbital is 2p subshell is partially filled with 1 electron each in 2px and 2py orbital. So now obviously the added electron should go to the 2pz orbital. So the added electron goes to the empty 2pz orbital with no repulsion. That's one reason. And this leads to a stable half-filled electronic configuration. So after adding, you get a stable electronic configuration, half-filled stable electronic configuration. And that is shown by the higher electron affinity value of minus 122 kilojoules per mole. And what about nitrogen? So nitrogen has a stable electronic configuration, 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and the 2p subshell is stable with half-filled electronic configuration. And the added electron goes to where? It goes to the 2px orbital. So already there is electron present in the 2px orbital, and this leads to repulsion. When you add an electron to an 2px orbital which is already occupied by an electron, it leads to repulsion. And repulsion, it's an energy demanding process. So you need to force or push an electron into 2px orbital in order to overcome this repulsion. And therefore it is a endothermic or energy demanding process which is reflected by the positive value. And what about oxygen? The unstable electron configuration of oxygen is 1s2, 2s2, 2p4, 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and total of 4 electrons in the 2p subshell. And after adding, where does the added electron go to? In case of oxygen, the added electron goes to the 2py orbital. And there is 2 pairing. After adding electron in the 2py orbital, there is 2 spin pairings, and this is favorable. Why it is favorable? So you may ask me, there is repulsion in 2 orbitals, 2px and 2py orbital. Yes, you are right. But this repulsion in 2 orbitals, that is 2px and 2py orbitals, is overcome or dominated by the increase in the effective nuclear charge, small atomic size, and moreover, oxygen just needs 2 electrons to complete the octet. So there are so many factors which is shadowing the electron-electron repulsion in the x and y orbitals. And therefore, it is shown by a exothermic process, negative value, 141 kilojoules per mole. What about fluorine? Now fluorine, unstable electronic configuration of 1s2, 2s2, 2p5, 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and the 2p subshell is almost filled. It just needs 1 electron to achieve an octet. So the added electron goes to the 2pz orbital, and that is to stable electronic configuration. So fluorine, it has attained a stable electronic configuration similar to that of the nearest noble gas neon, and therefore, and this is reflected by the high electron affinity value of minus 3 to 8. And I have not shown here the electronic affinity value for noble gas neon, because it's a noble gas and its electronic configuration is stable with the outermost shell completely filled with electrons. And it is the most stable of all the elements. Now let's take a closer look at the electron affinity trend in group 1 elements, that is alkali metals. Now going down the group, you know the trend. Electron affinity decreases going down a group. Lithium, sodium, potassium, rubidium, cesium, francium. So the electron affinity value decreases going down the group, which can be clearly seen in the values. Now, what are the factors affecting electron affinity values in case of group 1 elements? Now, as you go down the group, you see the number of electron shells or energy levels, they are increasing. So, as a result of this, the distance between the nucleus and the outermost electron shell increases, or the atomic radius increases. So, with the increase in the atomic radius, the electrostatic force of attraction between the positively charged protons and the outermost electron, negatively charged electron, decreases. So remember, the electron that is accepted by the atom goes to the, or it occupies the outermost shell. So because of the increase in the radius or the size, decrease the electrostatic force of attraction between the nuclear protons and the valence shell electrons, or the incoming electron which occupies the outermost shell, and therefore the electron affinity decreases and shielding increases. What is shielding? Shielding is phenomenon where the inner core electrons partially block or reduce the electrostatic force of attraction between the positively charged protons and the outermost valence electrons. And that is one part of it. So other aspect is the inner core electrons, they repel the incoming electron, negatively charged electron. And therefore, what happens? Effective nuclear charge decreases. What is effective nuclear charge? It is the electrostatic force of attraction between the positively charged protons and the outermost valence electrons. So the effective nuclear charge decreases going down the group because of increase in shielding. And what is the end result? End result is that as you go down the group, electron affinity value decreases. Why? Because as you go down the group, number of shells increase, radius increases, shielding increases, effective nuclear charge decreases, and finally electron affinity value decreases. So in summary, as you go down the group 1 elements will have low electron affinity values, indicating a low tendency to gain electrons and form negative ions. And this is due to what? This is due to large atomic size, high shielding, and low effective nuclear charge as you go down the group. So these factors, what I've explained so far, so these factors collectively contribute to the weak attraction for an additional electron in group 1 elements. And these are some of the general factors affecting electron affinity. That is, atomic radius is inversely proportional to electron affinity. Electron shielding is inversely proportional to electron affinity. Nuclear charge directly proportional to electron affinity. Electronic configuration. I would like to add a brief note on this important factor, that is electron configuration. Remember, atoms with stable electronic configuration will never accept the electron easily because it is already stable. It doesn't need an additional electron. Whereas only unstable, atoms with unstable electronic configuration, they have tendency to gain the electron. Why? Because they need an electron to increase the stability of the atom. So the general factors, these are the general factors not pertaining to the group 1. So increase in atomic radius, electron affinity decreases. Increase in shielding, electron affinity decreases. Increase in nuclear charge, electron affinity increases. So here I have highlighted this point because this point doesn't apply here when I'm going down the group. Why? Because going down the group, though the nuclear charge increases, the shielding also increases. So going down the group, the shielding wins over the nuclear charge, increased nuclear charge. So nuclear charge is directly proportional to electron affinity only going across the period, not going down the group. Now, electron affinity in halogens, group 7. Now halogens, as you know, it has a total of 7 valence electrons and it needs just 1 electron to fill its outermost shell. And going down the group, general trend, electron affinity decreases. The value should also decrease. But you see that the first two elements, the scenario changes for the first two elements. Fluorine has a lesser value as compared to chlorine. But as per the general trend, it should decrease going down the group. So the exceptional behavior is shown by the first two elements. Why is that? Let's find out. So fluorine has 2 shells, chlorine has 3 shells, bromine has 4 shells, so on and so forth. So we're not bothered about the other elements down the group. So let's focus our attention only on fluorine and chlorine because these two show anomalous behavior or exceptional behavior. Why is that? Now fluorine, its electronic configuration is 1s to 2s to 2p5. It has a smaller atomic size and electron density and crowding of electrons is more in the second energy level. And therefore there is less space in the second energy level or the second shell. And this leads to more repulsion between electrons. So there's more crowding, less space in the second energy level, more electrons in the second energy level, and therefore this leads to more repulsion between electrons. And when you add an electron, there is more repulsion between the added electron and the crowded second shell electrons. So there's a repulsion experienced by the incoming electron, and therefore there is a lower electron affinity. And what about chlorine? Why is chlorine showing a greater electron affinity? Because it has 3 shells. Though it has 3 shells, you can see the atomic size is bigger. It has more space in the third energy level. And there is less crowding of electrons in the third energy level. And there is less repulsion between electrons in the third energy level. And therefore, when you add an electron, the added electron experience less repulsion. So there is less repulsion between the added electron and the third shell electrons. And therefore, it readily accepts the electron. And therefore, the electron affinity in halogens is, in case of chlorine is more as compared to fluorine. So two major reasons, size and space. And let's take a look at the electron affinity in period 2 and period 3 elements. So let's compare and contrast the electron affinity values of period 2 and period 3 elements. So this is going to be a bit interesting. So this is just a continuation of what we had discussed just now. Why chlorine is having a higher electron affinity than fluorine. So chlorine is a period 3 element while fluorine is a period 2 element. So going across the period, electron affinity increases across the period. That's the general trend. And going down a group, electron affinity value decreases. But the electron affinity value of period 3 elements is more than the period 2 elements. Specifically with respect to group 4, 5, 6 and 7. I am stressing on these groups, group 4, 5, 6 and 7. So these 4 elements, that is first 2 elements. Remember, first 2 elements, that is period 2 and period 2. So only the period 2 and period 3 elements show this exceptional behavior. Only in case of group 4, 5, 6 and 7. So why is that? Let's find out. So in case of group 6 elements, that is period 2 and period 3 elements. So oxygen is period 2 element, sulfur is period 3 element. Fluorine is period 2 element, chlorine is period 3 element. So going by the trend, the electron affinity value should decrease, but you can see that sulfur is having a higher electron affinity value than oxygen. And chlorine is having a higher electron affinity value than fluorine, which I have already discussed. So oxygen, electron configuration is 1s to 2s to 2p4. It has a smaller atomic size and therefore electron density is more in the second energy level. There is crowding of electrons. So there is less space in the second energy level, more repulsion between added electron and crowded second shell electrons. And in case of sulfur, though the number of shells are more, it has more space. Electron configuration is 1s to 2s to 2p6, 3s to 3p4. It has more space in third energy level. So there is you can see there is less crowding of electron because of availability of more space and bigger size. So less repulsion between added electron and third shell electrons. Therefore, sulfur has a higher electron negativity, electron affinity value as compared to oxygen. So the same explanation holds good even for fluorine and chlorine. So the sulfur easily accepts the electron. It has more space and it is bigger in size. So same explanation holds good even for fluorine and chlorine, which I have already explained. So there is repulsion between the added electron and the second shell electrons because of small size and less space. So electron density is more in the second shell of fluorine atom. And chlorine, more space, bigger size, it readily accepts the electron, which I have already explained. So this trend you find only in case of group 4, 5, 6 and 7 elements. Not all the elements, only the first two elements, that is only the period 2 and period 3 elements. So what are those elements? You'll see the scenario changes only in carbon, silicon, nitrogen, phosphorus, oxygen, sulfur, fluorine and chlorine. You can just make a note of this, because questions will be asked in the examination only pertaining to elements showing exceptional behavior relating to a particular atomic property. Now, what do you get by understanding the electron affinity concept? So what is the takeaway? Now, by understanding the electron affinity concept, it helps one in predicting the chemical reactivity of the element. So elements with high electron affinity are more reactive and gain electrons to achieve stable electronic configuration, which you have seen in case of fluorine atom. So why fluorine atom accepts the electron to attain the stable electronic configuration. And also you can predict the type of bond an atom will form. So non-metals with high electron affinity like fluorine will gain electrons from metals with low electron affinity like lithium to attain a stable electronic configuration. And finally, they form a ionic bond. Like for example, fluorine reacts with lithium to form lithium fluoride, which is an ionic compound. Remember, fluorine does not exist it doesn't exist in the elemental form. It exists as a diatomic molecule. So bear this in mind. This is an important point. So fluorine, it doesn't exist in the elemental form, but rather it exists as a diatomic molecule. So fluorine gas reacts with solid lithium to form solid lithium fluoride, which is an ionic compound. And it also helps, electron affinity concept also helps one in predicting the behavior and properties of elements in various chemical reactions. Now I can summarize all these 3 points with the help of single reaction. So let me help you in summarizing all these 3 points with the help of single reaction. So lithium atom, it has one valence electron in its second shell. It is a metal with low electron affinity. Fluorine, it has 7 valence electrons in the outermost shell, second shell, and it needs 1 electron to attain the stable electronic configuration. So fluorine is a non-metal with high electron affinity. So lithium loses its outermost valence electron to the fluorine atom and forms a lithium ion, positively charged lithium ion. And fluorine atom, after accepting the electron given by lithium, it forms a negatively charged fluoride ion. End result is lithium fluoride is formed, which is a ionic compound, Li plus F minus. Now fluorine atom, that is lithium atom, before the reaction, its electronic configuration was 2-1, 2 electrons in the first shell, 1 electron in the second shell, and it attains the stable electronic configuration by losing its outermost valence electron. So lithium, after losing its outermost valence electron, it attains the stable electron configuration of helium, while fluorine, before reaction, it has electron configuration of 2-7, and after gaining an electron given by lithium, it attains the stable electronic configuration of neon, which is the nearest noble gas in the periodic table. So you can remember this particular reaction, and this reaction will help you in remembering or summarizing all the 3 points which I have highlighted here. So atoms become unstable if their outermost electron shell is incomplete and has high electron affinity, as in case of fluorine atom. So this has been a very lengthy video. Thank you for your patience and attention. Don't forget to subscribe my channel, share, like, and watch my full video. Thank you so much for watching my video. I hope you enjoyed it. I'll meet you in my next interesting tutoring session.